Imagine a massive thunderstorm, the kind that rumbles the ground and lights up the night sky with brilliant flashes. Now, push that image even further. Forget the familiar lightning striking downwards or even between clouds. Instead, picture a hidden light show, a secret spectacle unfolding far, far above, at the very edge of space in our planet's upper atmosphere. For decades, these were just fleeting whispers, uh, anecdotal reports from pilots, almost mythical in their rarity. But this hidden phenomenon actually has a name: transient luminous events, or TLEs. And in this deep dive, we're going to pull back the curtain on these extraordinary high-altitude electrical discharges. Our mission is to reveal what these TLEs are, how science has finally begun to observe and understand them, the incredible forces that create them, and maybe why their existence matters far beyond just the visual wonder. We'll explore the fascinating cast of characters in this atmospheric ballet, from the elusive to the truly gigantic. Okay, let's kick things off by making a really crucial distinction. TLEs are not your everyday lightning. When we say lightning, most of us picture bolts hitting the ground or flashing within clouds, right? But TLEs are a collective name for several types of short-lived electrical phenomena, or luminous plasma, that occur well above those normal thunderclouds. We're talking way higher. Typically, those clouds don't reach higher than about 15 kilometers. This is a whole different league.
Precisely. We're talking about discharges happening in parts of the atmosphere that, well, you'd usually consider pretty calm, far above where planes typically fly. And there isn't just one type. There are several main kinds of TLEs, each with its own unique look and, frankly, quite stunning appearance. The most famous ones are probably Sprites. Picture them as these huge, typically reddish-orange forms, although sometimes they can appear greenish-blue. Their shapes are incredibly varied. Some look like enormous jellyfish with long-hanging tendrils. People sometimes call those carrot sprites, which is quite descriptive, actually. Others are more column-like, or they have these arching branches. Often they start with a sort of diffuse red glow, a halo, way up high, maybe with structured blue streamers forming below that.
Jellyfish and carrots in the sky, way up there. That's pretty wild. And if I remember right, they're not just strange shapes, they're absolutely enormous.
Oh, absolutely enormous. Sprites develop up in the mesosphere, generally between 50 and 90 kilometers. That's about 30 to 55 miles above the Earth's surface. To give you a sense of scale, a single Sprite event can span altitudes from maybe 40 kilometers all the way up to 80 kilometers. And width-wise, we're talking several tens of kilometers, sometimes as much as 30 miles across. Imagine something the size of a small city just appearing for, well, milliseconds.
Wow. And you said they're different from regular lightning in terms of heat.
Yes, that's a key point. Unlike traditional lightning, which is incredibly hot plasma, Sprites are what we call cold plasma. Think of it less like a super hot spark and more like the gentle, sustained glow you get inside a fluorescent light tube. Electrons are excited, they produce light, but without that extreme heat.
Interesting. And the name Sprites, where did that come from?
Ah, that's a fun little anecdote. The name Sprites was actually coined by Dr. Davis Sentman from the University of Alaska. He was apparently inspired by mischievous Shakespearean characters, like Puck, Because they were so fleeting and hard to catch on camera, he thought they were elusive and tricky.
I like that. So after Sprites, what else is in this TLE family?
Well, then we have blue jets. As the name suggests, they're distinctively blue. That color comes from excited nitrogen gas. They look like narrow, cone-shaped jets of light shooting directly upward from the tops of thunderstorms. They reach altitudes of about 40 to 50 kilometers, so they're punching into the upper stratosphere. And they're very brief, too, usually lasting only a fraction of a second, maybe several hundred milliseconds.
Okay, so blue jets shoot up pretty high, but you mentioned gigantic ones, too. What about the gigantic jets?
Right, the gigantic jets. These are really the heavyweights of the jet category. They're among the brightest TLEs we see, but also the rarest, especially compared to blue jets. We tend to see them more often over oceanic thunderstorms, interestingly. They start deep within the core of a thunderstorm and rise much, much higher than blue jets. We're talking altitudes up to 70 or even 80 kilometers, sometimes reaching right into the ionosphere itself. And their upper part can actually change color, often from blue down low to red higher up. They can also last longer, nearly a full second sometimes, which is quite a long time for these events.
A full second. That's practically an eternity compared to the others. Okay, so we have Sprites, blue jets, gigantic jets. What else? You mentioned Elves.
Yes, Elves, and this is probably my favorite acronym in the field. Emission of light and very low-frequency perturbations due to electromagnetic pulse sources. Quite a mouthful. Elves typically look like huge, flat, expanding rings of light. Very diffuse. They can be enormous, hundreds of miles wide, sometimes up to 300 kilometers in diameter. From space, they often look like a giant donut expanding rapidly. They happen in the ionosphere, roughly 100 kilometers, about 60 miles above the ground, maybe a bit lower, 80, 90 kilometers along the bottom edge of the ionosphere.
A 300-kilometer donut of light. That's hard to even picture.
He said they're fast.
Incredibly fast. This is the truly mind-boggling part. Elves last less than 1,000th of a second, faster than 1 millisecond. That makes them completely impossible to see with the naked eye. I mean, it's faster than a camera shutter, faster than you can blink. It's almost instantaneous.
That's just, yeah, mind-boggling is the word. It sounds almost too brief to even matter.
Yeah.
Are there even more types, more obscure ones? Indeed there are. While Sprites, blue jets, gigantic jets, and Elves are the ones we've studied most, scientists have identified others. There are things called halos, which are brief descending glows, maybe 40 to 70 kilometers wide, and they sometimes appear just before a sprite. And then you get into the even more obscure and rather whimsically named ones like ghosts, which are described as faint greenish globes, and even things called trolls, pixies, and gnomes. The existence and nature of these are still really being explored. It seems the more we look up there, the more complex this hidden world becomes. It's like the atmosphere has its own secret folklore.
It really does sound like it. But it's clear these things are incredibly fleeting, super high up, and often hidden by the very storms creating them. So how on earth do scientists even begin to catch these? It sounds like a massive challenge, especially if some are faster than a millisecond.
It absolutely was a massive challenge for a very long time. For decades, really, all we had were these intermittent verbal reports. Pilots flying high, sometimes reporting strange flashes above storms, going back maybe even to the 19th century. But they were just anecdotes, easily dismissed. The real turning point came in 1989. It was actually quite accidental. A team from the University of Minnesota was testing a low-light television camera, pointing it at distant storms, and they just happened to capture this upward flash from the cloud tops. Serendipity.
Wow.
That unexpected image, that first photo of a sprite, was the eureka moment. It proved these things were real, and it really kicked off serious scientific interest and dedicated research efforts around the world.
That's a fantastic story. A classic case of accidental discovery opening a whole new field. So how did they go from that one lucky shot to actually studying them systematically from the ground, especially given how fast they are?
Well, ground-based observation campaigns became much more sophisticated pretty quickly. Groups like the Stanford VLELF group, for instance, developed specialized tools. They built things like photometric array imagers. One instrument was called Piper that could actually document hundreds of elves from just a single storm system. And to capture those really fast events, like the sub-millisecond elves, or to see the fine details inside sprites, they had to use incredibly high-speed video cameras. We're talking cameras recording at over 1,000 frames per second, sometimes much faster. That kind of time resolution is absolutely critical for dissecting something that lasts less than 1,000th of a second. They also use telescopic imaging to zoom in and reveal these tiny bead-like structures, the streamers, propagating in the lower parts of sprites.
Okay, ground-based tech got pretty advanced, but I imagine looking up through the whole atmosphere, often through clouds, must still be limiting. Space seems like the ultimate high ground for this, right?
It's exactly. Space-based observation became absolutely essential for getting consistent, detailed views. You're above the clouds, you have an unobstructed line of sight, you can cover huge areas of the planet.
Yeah.
The International Space Station, the ISS, has been a really vital platform for this. It's equipped with advanced cameras and dedicated sensors, like NASA's Lightning Imaging Sensor, or LIS, which was installed in 2017. And there's also the European Space Agency's Atmosphere-Space Interactions Monitor, ASIM, which was added in 2018. These instruments are giving us data we simply couldn't get from down here.
So what kind of cool stuff have we actually seen from the ISS? Any big moments or firsts?
Oh, several really notable ones. Back in September 2015, astronaut Andreas Mogensen captured what was described as a first-of-its-kind color video of a blue jet from the ISS cupola. He actually recorded 245 brief blue discharges over the Bay of Bengal, with one of them clearly shooting upward from about 16 kilometers altitude up to maybe 52 kilometers. Really dramatic footage. Then more recently, in February 2019, the ASIM instrument got this incredibly detailed look at a pulsating blue jet near the island of Nauru in the South Pacific. This event lasted only several hundred milliseconds, but again, it raced upwards from about 16 kilometers up to 52. What was really fascinating about the ASIM observation was that it also detected 5 intense blue flashes right below the jet, each lasting only about 10 microseconds. And one of those flashes seems to have actually generated the blue jet itself.
So it's like seeing the trigger mechanism almost.
Exactly. It suggests a complex sequence of events, not just a single discharge. And then there's the Thor Datus experiment, also on the ISS, which has logged imagery at almost 100,000 frames per second. That kind of speed gives us unbelievable resolution on the dynamics.
Incredible detail. Are there satellites specifically for TLEs too, besides the ISS instruments?
Yes, absolutely. Beyond the ISS, there have been dedicated satellite missions. For example, MIDEX flew on the Space Shuttle Columbia back in 2003. And the Isual instrument on Taiwan's Formosat 2 satellite provided a huge amount of data, especially on Elves, Halos, and Sprites over many years. And the research continues. ISIM is still operating, and there was a French mission called Taranis, designed specifically for TLEs, though it unfortunately failed after launch. But it shows the ongoing commitment to understanding these from space is definitely a hot area of atmospheric science.
Okay, now this is where it gets really interesting for me. We've seen what they look like, we know how we try to catch them, but what's actually causing these incredible light shows? What are the physical processes? It's clearly not just ordinary lightning taking a detour upwards, is it? What's the real mechanism?
You're right, it's not just diverted lightning. The mechanisms are quite distinct for each type. Let's start with Sprites. They are primarily triggered by very powerful positive cloud-to-ground lightning discharges. We often call those plus CGs. Now, these aren't your typical lightning strikes, which are mostly negative. Plus CGs are less common, but often much stronger, and they remove large amounts of positive charge from the upper parts of a thundercloud. It's quite striking. Actually, about 99% of all the Sprites we've observed are linked directly to these preceding plus CG strikes.
Okay, so it's specifically positive lightning, but is it just any positive strike, or does it have to be a particularly strong one? Does every plus CG make a sprite?
That's an excellent question. No, not every plus CG creates a sprite, but the really powerful ones often do. A key factor seems to be something called the charge moment change, or CMC. You can think of CMC as the sort of electrical oomph or leverage of the lightning strike.
Yeah.
It's calculated by multiplying the amount of charge removed by the altitude from which it was removed. And studies show that large CMCs, say greater than 300 Coulomb kilometers, have a very high probability, maybe around 75%, of generating a TLE, usually a sprite. So it's not just positive, it needs to be a positive strike that moves a lot of charge from high up in the cloud. That sets up the right electrical conditions above the storm.
Right, setting the stage. And how does the sprite itself actually form up there?
Well, the sprite forms in the mesosphere, typically between 75 and 80 kilometers altitude. In that region, the huge electric field created by that powerful plus CG below can actually exceed the breakdown strength of the thin air, causing the electrical discharge we see as the sprite. They're not solid things, though. They're actually composed of many, many individual streamers. These are like narrow, glowing channels of plasma, almost like tendrils, moving incredibly fast, maybe around 10 million meters per second downwards. That's over 3% of the speed of light. Wow. These streamers become brighter as they move down, and collectively they paint the larger shape of the sprite that our cameras capture. We also sometimes see long-delayed sprites, which can happen 10 milliseconds or even much longer after the lightning flash. These seem to be linked to a continuing current in the lightning channel after the main return stroke, like a sort of prolonged electrical connection to the ground. There was one amazing observation of a sprite appearing 144 milliseconds late, associated with a 16 kiloampere continuing current.
Fascinating. Okay, so that's sprites linked to powerful plus CGs. What about elves? You said they were different.
Completely different mechanism.
Yeah.
Elves are caused by the intense electromagnetic pulse, the EMP, that radiates outwards from any powerful lightning strike, positive or negative, cloud to ground, or even within the cloud. Think of the lightning channel acting like a giant radio antenna, suddenly broadcasting this incredibly powerful short burst of electromagnetic energy. This EMP travels upwards at the speed of light, and when it hits the lower edge of the ionosphere, it heats the electrons and excites nitrogen molecules there. That excitation causes them to emit light very briefly, creating the expanding ring or donut shape we see. The donut shape itself is actually predicted by models where you treat the vertical lightning channel like a simple antenna. The radiation pattern naturally creates that ring of maximum intensity at ionospheric heights.
So elves are more about the radio wave pulse from the lightning than the charge transfer itself.
Got it. And the jets, the blue and gigantic ones, how do they fit into this electrical picture? Yeah, the jets are different again. We can think of both blue and gigantic jets as types of upward electrical discharge. They represent ways for the storm to discharge electricity upwards into the atmosphere rather than downwards to the ground. They're fundamentally linked to charge imbalances within the storm cloud itself, almost like an electrical pressure release valve for the storm.
Okay, so how does that work for blue jets specifically?
Blue jets seem to happen because of an electrical breakdown between the main positive charge region, often found in the upper part of a storm cloud, and a layer of negative charge called a screening layer that gets tracked to the very top of the cloud from the surrounding atmosphere. Think of it like a hidden negative shield forming just above the cloud top. When the charge difference between the cloud's upper positive region and this negative screening layer gets large enough, you get a discharge of the blue jet punching upwards through that layer. They often happen quite quickly, maybe 5 to 10 seconds or less, after some other lightning activity has suddenly changed the charge balance inside the storm. And specifically, positive blue jets are known to transport positive charge upwards.
And gigantic jets, how are they different from blue jets in terms of cause?
Gigantic jets seem to start more like a normal lightning flash between charge regions inside the cloud, maybe between the main negative charge region in the middle and the positive charge region up top. But then, instead of staying within the cloud or going to ground, this discharge channel finds a path out the top of the storm and just keeps going upwards, much higher than a blue jet. So they represent an alternative way for the storm to get rid of that big mid-level negative charge. Instead of sending it to the ground via negative lightning, it sends it straight up towards the ionosphere. And the amount of charge they can move is really quite staggering. As I mentioned, there was one observation of a gigantic jet transferring negative 144 coulombs of charge way up high. That's easily comparable to the charge moved by a strong lightning strike to the ground, but it's going in the completely opposite direction.
Okay, that paints a clearer picture of the how, but it brings us back to the so what question. Why should we, down here, care about these dazzling but incredibly distant flashes? What's the bigger relevance of understanding TLEs?
That's the crucial connection, isn't it? Beyond just being amazing natural phenomena, TLEs actually have some important implications for our planet's atmosphere and potentially for us. First off, let's talk about atmospheric chemistry. TLEs are recognized as a source, although the exact amount is still debated, of NOx. That's nitrogen oxides like NO and NO2. And NOx compounds are important because they play a significant role in the chemistry of the middle atmosphere, especially in influencing the concentrations of ozone, O3, and the hydroxyl radical OH, which are key atmospheric cleaners and regulators.
Right. NOx and ozone chemistry is complex. You said the amount is debated. What's the uncertainty there?
Well, some studies using models and observations do suggest that you can get significant local increases in things like NO2, maybe a 10% bump, at around 52 kilometers altitude, right above very active thunderstorms, producing lots of TLEs. However, when scientists look at the bigger picture, the global scale, the current thinking is that there's no evidence of any significant increase in NOx on a global scale. They can be attributed solely to TLEs. So while they definitely contribute locally, their overall global impact on atmospheric chemistry seems to be less dominant than other sources like emissions from the surface or regular lightning lower down.
Okay, so a local chemical impact, but maybe not a global game changer. What about energy? Are they moving significant amounts of energy around?
Yes, definitely. That's another key aspect. Energy transfer. TLEs are a very direct mechanism for moving huge amounts of energy from the troposphere, where the thunderstorms are up into the middle atmosphere, the mesosphere, and even the lower ionosphere. The energy involved can be quite substantial. Estimates for the average energy deposited by a single Sprite event are around, say, 22 megajoules. Though, I should add, those estimates vary wildly. In the literature, you see figures ranging from just 1 megajoule all the way up to a staggering 40 gigajoules for some events. Regardless of the exact number, it highlights that these seemingly brief flashes are actually powerful conduits, funneling significant energy upwards, which has implications for the energy balance of those upper atmospheric regions.
And does this upward energy and charge transfer connect to anything broader, like the Earth's overall electrical environment?
It absolutely does. That brings us to the global electric circuit. You can think of the Earth and its atmosphere as a giant electrical circuit with the potential difference between the ground and the ionosphere and currents flowing through the atmosphere. TLEs, particularly gigantic jets, play a role in this. By transferring large amounts of negative charge upwards to the lower ionosphere, gigantic jets effectively discharge the global circuit, momentarily reducing that potential difference. Similarly, those powerful positive plus CG lightning strikes that produce sprites move hundreds of coulombs of positive charge down to the ground, which also affects the circuit. Even though these individual events are relatively infrequent compared to normal lightning, a single large TLE event like a big gigantic jet or a sprite-producing storm can potentially transfer something like 0.1% of the total charge stored in the entire global electric circuit. So while maybe not dominant in the long-term average, they have profound short-term transient effects on this planetary scale electrical system.
Wow, 0.1% from a single event is actually pretty significant. Okay, so chemistry, energy, global circuit. Are there any direct, maybe more practical implications for us or our technology?
Yes, there are potential real-world impacts we need to consider. For one, TLEs, especially the EMPs associated with Elves and the intense fields from Sprites, can impact communications on the ground. They could potentially interfere with very low-frequency, VLF radio waves used for navigation and other purposes, or perhaps even affect satellite communications passing through those regions. Also, given their high altitude and the powerful electrical discharges involved, they may even present potential dangers for aircraft, especially high-altitude research planes or balloons, and even spacecraft passing through those upper atmospheric layers during a major TLE event. The risk is likely low, but it's not zero. And maybe more broadly, just having a better understanding of what causes TLEs and how they connect to thunderstorms may also help scientists improve our ability to forecast weather. By incorporating these upper atmospheric electrical processes into our atmospheric models, we might generate more accurate simulations, ultimately expanding our overall understanding of everything happening in Earth's skies from the ground up to space. They're not just pretty lights. They are pieces of a much larger atmospheric puzzle.
It really feels like we've journeyed from familiar thunderstorms near the ground all the way up to the edge of space, uncovering this hidden world of luminous events. They seem just as scientifically important as they are visually spectacular, aren't they? It's truly amazing to think about these dynamic, hidden forces constantly at play right above our heads.
Absolutely, and it's crucial to remember this journey of discovery is really far from over. While we've made tremendous progress, especially in the last few decades, so many questions still remain. For instance, the exact mechanisms of initiation and propagation of sprite streamers, those incredibly fast tendrils, are still being actively researched and debated. We see them, we know they're fast, but the precise physics of how they start and move at those speeds is still not fully nailed down. There's also a real need for higher resolution spectral measurements. That means getting better data on the different colors or wavelengths of light within TLEs, which would allow for more accurate calculations of their temperature and chemistry. And we definitely need maybe 100 times better time resolution and even faster cameras to resolve many missing details, particularly in the very rapid evolution of blue and gigantic jets. The more closely we look and the better our tools become, the more intricate and fascinating this whole picture gets.
So maybe the next time you see a distant thunderstorm flickering on the horizon, take a moment. Imagine that secret light show, that silent, spectacular ballet of sprites, jets, and elves unfolding high, high above it. It makes you wonder, doesn't it? What other hidden wonders are constantly playing out just beyond the reach of our everyday senses, waiting for us to find the right way to look? And what new understanding of our dynamic planet will they unlock next?